All right. It's good to be back at a conference. This is very strange for me. It's been like 2 years and I haven't done this, so just a bit rusty. I apologize. It's my fault. It's all my fault. But I'm really excited to be here. I am incredibly excited to be here. My name's Chandler. I do lots of C++ things. But today I have an interesting talk. This is not really the title of the talk, though. The real title of the talk is a question. C++. What comes next? A bunch of you think that you know the answer. I don't actually know the answer. This is the answer. I don't know. And this talk is going to try and dig into why we don't know and what we can do about this, because I think this is actually a question we should have an answer to. When I say what comes next, right, we've had a lot of other programming languages that have gone through transitions over the years, right? But when we come down to C++, we have these question marks, and I have no idea what needs to go into these question marks. So how do we answer this question? How do you even make progress on answering this question? Well, I like to go back to our goals. I always like to start with our goals, or what problem we're trying to solve when we're talking about what comes next. What is it that we actually want to do with C++? Titus and I gave a great talk, and Titus even referenced it yesterday. It's almost like we talk a lot about what C++ is, and we try to really dig into our goals for C++. I'm not going to try and go into as much detail. It's a fun talk if you want to watch it. But at the highest level, our goals for C++ are performance-critical software, software and language evolution, code that's easy to read, understand, and write, practical safety and testing, like fast and scalable development, have to support all the modern operating systems, hardware, different environments. We wrote these up in a paper for the C++ Standards Committee years ago. This isn't new. And these are still our goals today. But the problem we're trying to solve is that C++ is still falling short of these goals. It's not doing as well as we would like. Now, I can get up here and give you a million examples of why. You probably already have your own ideas in your head of where it is that you think C++ falls short. Titus gave a talk yesterday talking about places where C++ falls short. My question is, why? Why is C++ falling short of whatever goals we have for it? What's the root cause? And I think that the initial root cause is that C++ has been accumulating just decades of technical debt. Right? It started off with decades of technical debt when it inherited the debt of C. We got textual preprocessing. We got absolutely bizarre operator overloading rules and precedence rules. We've gotten integer promotions. I mean, we can go on and on and on. There was a tremendous amount of technical debt that no one wanted to change. And it wasn't like C++ made a mistake. This was not a mistake. This was an excellent decision to take on this technical debt. It was expensive, but it was probably the right call. By inheriting all of C, C++ actually bootstrapped its entire ecosystem. This was essential to its success, especially at the time. C++ then coupled this with one other decision that I think is the part of the root cause of this, and that is prioritizing backwards compatibility. And this has caused C++ to continuously add more technical debt to the language. I mean, we put co_ in front of all of our keywords because we are terrified of breaking existing code. And understandably, breaking code is actually really expensive. It's really disruptive. Backwards compatibility is a huge feature, but it also is very expensive. And it's not just that we add new technical debt. Backwards compatibility prevents us from fixing the technical debt we already have. So we started off with C's technical debt. We continually add more, and we have a priority that means we can't really fix any of it. This is not a recipe for success. Okay? And I think this is the root cause for C++'s technical debt and a lot of the other problems that C++ faces today. Unfortunately, there's another factor that compounds it, and that's the process by which C++ has evolved. And this process is something very constrained, right? C++ is part of ISO. ISO has very, very strict rules about how things work. And it's interesting to think about what motivates the rules of ISO. Like, what is ISO trying to achieve with these rules? ISO is trying to achieve representation of nations and corporations in the establishing of standards. That's a perfectly reasonable goal, and I actually think ISO's process is pretty reasonable to achieve that goal. If that's your goal, ISO makes some sense. But I think it's a very different goal from making complex design decisions to address complicated technical problems like the technical debt that is currently all over the C++ programming language. If you want a group of people to do that, I would not prioritize representation of nations and corporations. I would prioritize psychological safety and a really effective team with, some really good experts that has a good decision-making process, that can move fast and quickly evaluate different options, right? That would have, a way to experiment. All of these things make sense, but they don't make sense for ISO, and because C++ is part of ISO, they're not really available. I think that makes all of this much more difficult to fix within C++. So this is kind of a downer. What are our options? Well, there are a bunch of really great programming languages out there. Tons of them. Unfortunately, most of them are garbage collected. And to be fair, garbage collected languages are kind of amazing. They're wonderful. They're simple languages, they just work, they don't have a lot of the complexities of other programming languages. You can easily use them and they do the right thing. They're safe, they're reliable, but they have some performance cost, right? You pay for that. You pay for that simplicity, that ease with the performance overhead. And for many users, that's a great trade-off. You should absolutely make it. If you can afford to spend a little bit of your compute resources on using a garbage collected language, that's fantastic, right? But some of us can't. There are some users who really need every single bit of the performance that C++ affords us. So these aren't good options there. Of course, a bunch of people would say, Rust, it's Rust. I hate to break it to you all, this is not a Rust talk, just for the record. But Rust seems like it might fit here. It's really, really interesting language. But if you look at the other languages on this, right, from C++ to TypeScript, Swift, and Kotlin, Rust doesn't actually fit really well. That's actually not anything about Rust. Rust is a great programming language. And again, if Rust actually solves your problem, if it's a good tool for you to use, please use it. It's a fantastic programming language. I'm super impressed by everything that the Rust community and the Rust team are doing. But if you have a very large C++ ecosystem, and you have very deep dependencies on it, moving that to Rust is going to be extremely difficult. Okay, so if Rust isn't gonna work, and garbage collected languages aren't working, what other approaches do we have? Let's dig a little bit more deeply into these historical languages. So C to C++, JavaScript to TypeScript, both of these are really interesting. These are kind of superset languages. Both C++ and TypeScript took the entire existing thing, you can just map it into the new language, no problem at all. Swift changed it up a little bit. Swift is a kind of brand new language, but it had an interoperability bridge into Objective-C. Also had a bunch of other confusing things that complicate things. Swift is kind of a different beast. But it started to explore a different way to move from one language ecosystem to another. And I think Kotlin's really nailed this idea. Because here we have a new language, right? It doesn't try and include all of Java. But Java feels natural. It fits. You can take your Java code, use it in Kotlin, and it doesn't feel like you're, really bending over backwards to try and make it work. It's not contorted. It fits very naturally. And you can even turn that around. You can use Kotlin code from Java, right? It's a really, really seamless interoperability story that allows Kotlin to build on the Java ecosystem without including all of Java and making itself a superset. So I think this is a super interesting pattern, and there's a common thread for each one of these languages, and that's that each one was designed for the purpose. Each one of these languages was very intentional when it was being designed that they wanted to build on top of an existing ecosystem, right? They didn't want to start a new one. And I try to call these successor languages, right? When we talk about a successor language, we build on an existing ecosystem, provide bidirectional interoperability, optimize the learning curve and the adoption path, and I think ideally you should have tool-assisted migration support. And when you put these together, you have a pretty compelling way to introduce a new language that builds on top of an existing one. And this isn't even a new idea. If any of this sounds super familiar, it should. Herb talked about this at ACCU. He gave this exact same analogy. Now his talk focused on the superset case. Because when you're a superset, your compatibility, your interoperability, it's perfect, right? It's just perfect by being a superset. I'm a little bit more interested in the Kotlin design, which isn't a superset, and it doesn't have as perfect of interoperability, but has a different freedom. It gets to make more sweeping changes. It gets to make more dramatic improvements. I think that's really compelling. But we don't have one of these that fits in these question marks. This doesn't exist. There's not a good language today that I can fit into those question marks that takes this successor language approach in order to be a compelling option for current C++ users. And a few of us thought, this is really too interesting to leave this way. This is something we need to explore. So we started building something that would fit into these. We're calling it the Carbon language. The idea is an experimental successor to C++. Okay, so how does this work? How do we have an experimental successor? We take the goals that we have for C++, like the original 6 goals, but now we have to add a critical 7th goal: interoperability and migration from existing C++ code, right? We have to tie back to the existing ecosystem. And there are 3 things here that I think are gonna really allow Carbon to address the things that have made C++ really have a difficult time. That's the interoperability, migration, and language evolution. So let's look at these 3. Interoperability. The key thing about interoperability is we don't inherit all of C++'s technical debt. We get to start a little bit fresh and use an interoperability basis to access the existing ecosystem. With migration, we can provide some dramatic immediate improvements to code. When you actually move from one to the other, we can really level you up. We can, have the pointers actually treat nullability as part of the type system and fix the however many $1 million bug it's gotten to at this point. We can actually remove confusing integer promotion rules. We can clean up the expression semantics. There's a ton of opportunity to immediately level up your code and the experience you have. But that's not enough. If we just have one step function, that's not enough. We need something better than that. We actually need to sustain these improvements. And so we need a language evolution model. And I specifically think we need one that isn't focused on backwards compatibility and is instead using tool-based upgrades as the language improves. Continuous tool-based upgrades as the language improves. If we combine these, I think we have a really compelling option here. So let's dive into what this would look like if we were to pull these together and what kinds of things you could expect. First thing, I think we just have to clean up the grammar. I don't know if anyone's worked on a C++ parser, but it's miserable. If you've ever worked on an IDE for C++ or something that doesn't get to really be a full compiler, it's incredibly difficult. We can make that better by simplifying the grammar and making it easy to parse. This doesn't take a lot of wild new technology. We can just use introducer keywords. So here we use a keyword fn to introduce a function. Use the var keyword to introduce a variable declaration. And with this variable declaration, we get to fix something really phenomenal, right? I don't know if you all realize this. On Wikipedia, the most vexing parse, there's no qualifier for language, the most vexing parse is a C++ parse, right? And that's just not okay, right? But we can fix this. We know how to fix this and build a grammar that's friendly to humans and also friendly to the parser. We can keep going, so we can use the name and then a colon and then the type and a pretty standard structure here. And this also is easier to parse. This also is much easier for the compiler to handle, but it's also good for humans. Humans like this kind of syntax. I also think we can have function inputs as a first-class property of the language, something that the language directly provides tools to address. We actually have already seen these, right? We have a circle input here and a log2scale input. And these kinds of function parameters are the ones that in C++ you have this really frustrating choice to make every time you use one. You're like, well, I can use a const reference and I won't have any copies that I didn't want, which is nice, that's good, but it won't pass it in register, which is a little unfortunate if it's a 32-bit integer. Or I can use by value, which is great, it'll pass it in register, it's really efficient, but it'll also force a copy, and sometimes that could be really expensive. And if you're writing generic code, then you just don't have any good options, right? Because you have to pick one of them, and you know that there are these other types for which it's not the right answer. But the language can address this. We can just provide a tool that very directly addresses this and expresses the intent. We can even make it short and easy to write. We can unify all of our indirect and mutation access around pointers, collapsing all of the references and the 3 or 4 different kinds of references into a single part of the type system. And pointers are fundamentally simpler than other things because you can actually refer to the pointer separately from the pointee, something you can't really do with other constructs. And we actually are using this here too. We have an input-output parameter, a results vector, right? And we pass this as a pointer. That means that down here we actually use pointers to indirectly update our caller's results vector. We can also use expressions to name types. I don't know if you've used C++'s templates in Anger a little bit, but there's this whole other grammar for how to name types in C++. There's some exciting parsing problems within it. It can be really, really frustrating. We don't need a second grammar here. We can reuse the expression grammar. And we're actually, again, already doing this. We have circle. This is just an expression. It references a global circle. And we have I32. This is also an expression. It's kind of actually like the expression 32. This is a literal that gives you a type. Then we have something more interesting. If we have a parameterized type, like C++'s std vector, right, we can actually use function call syntax for that to say this is a vector of 32-bit floating point types. Make sense? Another place we can simplify is the global namespace. I don't know if folks have worked on large code bases, but like at Google, we spent about a decade doing really terrible things in the global namespace because there was no guardrail in the language to stop us. It was so easy to put things into it, and then ODR and other chaos ensues. We don't have to have that kind of problem. We can actually make sure that the namespace at the root of your files is always local, so we make it local to a package of source code. And so when you start your file off, you immediately say, this is a package and its name is geometry. And now the namespace for all of this code is geometry. There's no single global namespace. You don't have this single merge point that every single file has to agree on. It's now localized. We can import APIs through their package name. C++ has been working on this with modules, and we can kind of fully internalize that and bake it into the language at a very deep level. Right, and so when we come in and we want to import some library from the math package, we say import math. And remember, each package is within its own namespace, and so this import just introduces the name that it mentions, math. Right, everything else is below that. If we want to get at pi, we do math.pi to get at it. And so there's no kind of action at a distance. We're not injecting things into your namespace that you weren't prepared for. Another simplification, and this one actually surprised me, I did not see this one coming, was to make members public by default, and then just allow you to declare them as private if you want to. This seems super counterintuitive to me. It seemed like the default should not be public, right? You want to be very intentional in what's your public API. But then, if you think more about it, what are you going to read most? You're going to read the public functions in your API more than any other functions, right? All of your users are going to be staring at these. This is the perfect place to optimize for the reader, to remove some line noise, take the extra keywords out. And of course, we can still put a private keyword onto a member in order to mark it as private. We can use something that C++ has been experimenting with, explicit object parameters. We just started to get this under a somewhat surprising name of deduced this. But we're starting to get explicit object parameters in C++. And again, this is something we can internalize and bake all the way into the language. And when we do, it gives us a nice functional way to differentiate between methods and non-methods, right, or static member functions in C++. And so in Carbon, we have a factory function. This isn't a method. It doesn't accept any object parameter. It's a factory. It returns a news article. And then when we want a method, we can add an implicit object parameter. We know that it's that because we put the little me keyword in there. Now, some of you may think this me keyword is really goofy, and it kind of is. We were liking this at first. I think actually at this point, no one is really fond of me. I suspect that whole language evolution thing is going to get tested here, and we're going to change this to a different one. But you have a keyword that identifies the object parameter, right? We have the parameter type. And already we get to use other things that we're simplifying, so we get that read-only parameter, and all of the optimizations from it are now available for methods because we have an explicit object type. And this works just like you would expect, right? Articles, passed in there. And when we need to do a mutating method, right? It's interesting to think about a mutating method. It's really not mutating its own object, it's mutating the caller's object. It is actually kind of an indirect operation. And so we model that as a pointer to be consistent with the rest of the language. But this is one place where having a pointer does create an ergonomic burden compared to references. And so we added language support to address the ergonomic problem. And it's this adder keyword. And what this says is whenever you're going to call this method, right, we see the method and we're like, oh, hold on. For this method, we're going to take the address of the implicit object parameter before we pass it in. And that way you can actually take it by pointer, you can mutate it, you have that capability. And so the call looks just like a normal method call, right? All of this is handled in the declaration. We do have inheritance. It's not too fancy, this is pretty easy to understand. We just tried to simplify and focus inheritance on the single inheritance use case and do some basic cleanups like making classes final by default. And so we can start off with direct language support for abstract types. You say you want an abstract class, you get one. You don't invent a method here. You can have a base class if you want something that you can instantiate, but you can also derive from. And then we have final classes that just can't be extended any further. Of course, final classes can still extend other classes. We can use keywords to make this a little bit more readable. We also try to clean up other keywords, so there's just an abstract keyword to mark abstract methods. We use impl, and it's in a consistent position. Virtual works basically the way you would expect. Nothing too remarkable here. But single inheritance doesn't cover all of the use cases. There are real use cases for multiple inheritance. And some of them we actually think would be better served by a totally different thing. So let's talk about powerful definition checked generics. Now when we talk about generics or generic programming in C++, we usually talk about templates, right? And maybe with C++20 you start talking about concepts with templates. But there's something more powerful than the concepts we got in C++20. If you go back to C++OX, there was a concepts effort that was much more powerful and actually gave you, I think, a more true form of generic programming. And you can see versions of this in modern languages like Swift and like Rust, where we have powerful definition-checked generics. And we want to have something with the same capabilities in Carbon. In order to have this powerful definition-checked generic, you first have to define the interfaces you type check against, okay? This is like a concept in C++ or a trait in Rust. We call them interfaces, right? This is a summary interface, has a summarized method that you have to implement. It returns a string. And this is enough information for us to type check code that uses this interface. So when you have a generic function, like print summary, it's going to accept both a type parameter and a runtime parameter. The type parameter is marked with an exclamation point, right? This says that this is actually a generic type parameter, T. We say that it's constrained to implement this summary interface. This tells us how we want to type check uses of T. We put it in these square brackets, and that marks that this is actually deduced. You don't pass this explicitly. This has to be deduced from the runtime parameters. We can see that that's X, which is our runtime parameter, and then T, where we can deduce it. And what this lets us do is we get to come down and actually type check the entire body of this function, right? We know exactly that X must have a summarized method because the summary interface said so. We know that the return type is string because the summary interface said so. We can completely type check the body of this function, and we don't ever have to revisit it. No matter which type you plug in here, we know that the body of this function is correct. So how do you implement these interfaces? How do you use them? Well, we want these to be implemented explicitly, not structurally, so that if the interface carries semantics beyond the exact signature, you actually are choosing to be part of that semantic model. So if you have a news article, maybe it wants to implement, this summary interface. So you say that you're going to implement news article as summary, right? News article is implicit because you're inside the class body. And then you have to give a definition of that method. And this lets you come down and take a news article parameter, and you can call print summary. And when we call print summary here, we're not type checking print summary's body. We already know it's correct. All we're checking is, does the type of news article implement summary? Just yes or no question. If yes, this is correct every time. If no, there's an error and it's right here. It's not an error somewhere else. There's not a backtrace. It's an immediate error. And because we put this method inside the body of the class, it's still a method on that class, and so you can just call it. No problem at all. But what about types that you don't own, and you can't open up the body of the class and put a method inside of it? Interfaces also give us a way to do API extension points. And this lets us get to another piece of technical debt in C++. We don't have ADL. We don't have the ADL-based overload selection as extension point mechanism, whether you wanted it or not. And so instead, we maybe are importing a tweet class from another package, right? And then we want to come down and we actually want to give an external implementation of this generic interface, right? And so this is external because I can't modify tweet. Tweet already exists. I can't touch it anymore. But I can externally say that tweet is going to be implemented as summary. And when I do, I can come down and take a tweet parameter. I can call print summary. And again, all we're going to check here is, well, does the type of T, tweet, implement summary? And yeah, it implements it right above. You can't do this in every location because we don't want to get another piece of technical debt from C++, no diagnostic required, one definition rule violations, or ODR, NDR. It's a very confusing set of acronyms. But we don't want these. This is a really thorny problem where in C++ you can write code and you have no idea if it's correct and no tool tells you whether it's correct and you just run your program and sometimes it works and sometimes it doesn't. And that doesn't seem like a good experience. And we can do better than that. We restrict these external impulses to only occur either with the type or tweet or with the interface summary. Has to come with one of those two. So this is our interface summary, so we get to do an external import, even though tweet is not our type. Okay. That was a lot of language nerding. Hopefully you're at least a little bit intrigued. There is so much more that I have no time to go into. I've just given kind of a sampling of pieces and bits and pieces, but there's something we haven't talked about that's maybe more important than all of this stuff, and that's interop, right? Because that's kind of the key thing. So let's get some C++ back up on the screen. So we have a C++ header, and I apologize, this is really simple code. I wanted it to fit on a slide. So we have a C++ header, it's a circle. Now, how do we use that from within Carbon? Well, we just import from the CPP package circle, the header file. And what we do behind the scenes is we fire up a C++ front end, Clang is the one I would like to use, and we go and we parse all the C++ code as C++ code, no fancy other thing going on there. And we build a C++ header module out of it. Once we have the C++ header module, we can look at that AST, and we can walk over it and synthesize a Carbon AST that maps into it. And then that's the thing we actually import semantically, okay? And so this is how we build that interop bridge. And the compiler handles all of the messy parts, and you get this really simple model where you just, if you want some C++ code, you just import the library. There's no problem at all. And now we have cpp.circle. Again, we have this package rule in Carbon, and we kind of put C++ within that to have a nice clean site. So it's a cpp.circle here. We can get an object of it. We can get it members of it. It's the C++ object. There's not any overhead here. We're just completely representing the C++ object for you inside of Carbon. But that's only one direction. We can do the other direction as well. So we can have some C++ code, and it's just normal looking C++ code. But it's going to include a header file that looks very strange, right? Because we didn't write this header file. This is a synthetic header file. And so when Clang, again, comes along and it sees you're including this, Carbon header file thing, it's like, hold on. I know about this because there's a Carbon module over here, right? And it goes and it loads up that Carbon module, takes that AST, walks over it, and synthesizes a C++ AST that will map back into the Carbon one. And then it imports that as a Clang header module. Right? And because we have modules in Clang that can just transparently take the place of header files, this can actually work, and it can be very intuitive and very clean. Okay? And once you do this, I have a geometry namespace, right? We said that packages were always in their namespace, so this is geometry. And then I have a print area function, and I can just call it. We can even provide a bunch of implicit conversions for whatever Carbon slice type looks like, so that you can do the kind of standard conversions you would expect so that your APIs actually work in a friendly and accessible way as you move back and forth from Carbon to C++, back and forth, back and forth. All right. We've talked about interoperability. We've talked about kind of that big improvement we want to make with migration. There's something we haven't covered yet, right? And that's the process. because if we do all of this and we actually still don't know how to actually make this language move forward, we're gonna get right back to where we are with C++, right? Sure, we'll have a few years of really happy times with low technical debt, and then we'll be right back to where we started. So let's talk a little bit about the project, the process, how we want to orchestrate this whole thing. First and foremost, community and culture. I absolutely love this quote. Culture eats strategy for breakfast, technology for lunch, and products for dinner, and soon thereafter, everything else too. This is a quote from Peter Drucker, it's a business person, right? He's talking about corporate culture, but I think it applies basically everywhere, right? And so when we're talking about community and culture and how important is it, it's the most important thing, right? Everything else follows this if we get this right. So we want to have an inclusive and welcoming culture. We want a comprehensive code of conduct. We want a friendly and approachable community. And this has been really hard. Programming languages, I hate to say it, but programming languages, and not just C++, they have a bad reputation, right? They are not easy communities to get into for outsiders. They're not the most welcoming, the most accessible communities. We want to try and help change that. We know that we have to overcome that. We've got to really invest and work hard on this in order to be super, super friendly, super, super approachable. Another part of that is having kind of an open process and governance model. Like when we're changing things, people need to understand how and why we're making changes, what went into it, what factors we're considering, how can they participate. That has to be open, that has to be transparent. We need to make decisions with a clear rationale, not just because like, well, today I really like left. So we're gonna go left today. Like you need a reason to go a direction. You need to explain why it's happening so that people understand it, and even if they don't agree, they do understand and they can work with the decisions you're making. We also want to try and set ourselves up for a batteries included tools and ecosystem world, right? We don't want to just have a specification or just have a compiler. We want all of these things to be in scope. We want to have documentation be in scope, user guides, tutorials, developer tools, IDE tooling. If it makes sense to include, we want to include it because we really want to provide a great experience for developers out of the box. And yes, that should include a package manager, eventually. but eventually, because we're so early right now. All of this is setting up our scope. You know, we don't have a package manager. We're not gonna have a package manager for years. We don't even have a tool chain yet, okay? So don't get ahead of yourselves, but we really do wanna have this door open. We want to be open to these kinds of things in our ecosystem and in our tooling. We're trying to follow a modern open source development model. Nothing too surprising here, but this is kind of the different way of actually orchestrating the work compared to an ISO process. Using LLVM's license, a CLA, we're doing almost all of our development on GitHub. We use Discord for chatting. We actually tend to use a lot of tools whenever they make us more productive. So we even use Google Docs for collaborative editing and video conferences, all kinds of things. The evolution process, it's really just GitHub pull requests. That's it. If you want to make a change to the compiler to fix a bug, you send a pull request. If you want to change the design, you actually send a pull request. If you want to suggest that the project needs a different goal, that's also a pull request. Now, the bigger changes, we're going to ask you to write in that pull request some rationale for why we're making the change, right? What factors went into it, but it all just starts with the pull request. And the pull requests are approved starting with just normal code review. We don't have the second process. If it's a simple change, we do code review, it lands, there's nothing else that goes on here. For some bigger changes, when we're doing something really significant, or when we're trying to make a tough decision and there's not any consensus in the community, we do need a governance process, though. We need a way to make decisions. And our current governance process is a group of 3 leads. That's myself, Kate Gregory, and Richard Smith. And these are 3 leads that are basically asked to put on a lead hat and make decisions, right? They can't actually contribute much to the design. They can only look at a set of options that are presented to them by the community and say, yeah, that looks good, or no, that doesn't actually align with the goals we have. Or if we get 2 options, we can be like, well, A or B, right? Those are the choices that they get to make. They don't get to do other things. So where is Carbon today? We have a bunch of people that have been contributing for a little while, but it still is technically a small group. We do have some companies that are involved, Google and Adobe. We have Indiana University that is, has a research group there. And the thing is, this is a great group of people, but we really need to go further. So our current goals and focus, number one, going public. Hi, everybody. Two is trying to complete the language design. And third is to develop a demo implementation of this core language design. When I say the core language design, I mean basically the minimum viable product, like the minimum thing we could really evaluate in this space. It's sadly kind of huge because it has to have C++ interoperability. And that means it has to front load a tremendous amount of work. Generics, all kinds of other things have to be front loaded. But with that, I think the next thing we should really do is something a little bit more exciting like live demo, because we do actually have a demo implementation. And so with that, and it's actually called the Carbon Explorer with the blessing and encouragement of Matt Godbolt, who's been working with us on some of these things. We discovered kind of after the fact that we had ended up replicating the Compiler Explorer workflow in our demo implementation of Carbon. And it just seemed like a really great name. And so I'm going to now try to demo Carbon Explorer. Hopefully you folks can see this. Maybe. So first off, let's look at my Carbon code. I have your classic hello world example here. And I'm going to fire up my Explorer. And it runs. I know, it's not that exciting, right? Let's do a slightly more exciting example. So I have a much larger thing. You might recognize some of this code. This is basically the news article example. Right, we have some actual code here. So let's try this one. This one's a little bit more exciting. Okay. So it is an interpreter, but it is starting off by compiling. Now, we haven't invested a lot in nice diagnostics because this is just a demo for us to understand the language. But it is telling me that, this method publish isn't going to work. Why is that? Well, I have a let here, right? And this let is not going to let publish mutate it. If I look up publish, it needs to take the address of its object. And let is like a function input. It's this read-only thing. You can't take its address. It has to be passed around by value. So if I want this to compile, I have to change let to var, and then compiles, and it says hello. That's kind of interesting, but we can do a little bit more here. So we might also want to know, like, did that publish actually work? Something like this. We have a little if expression in here. If I didn't have too many typos, maybe, if I save. Hey, it says that it's published. And so now if I comment this out, right, it's not published, and because I commented it out, now I'm not mutating the object. I can actually go back and just make this a read-only object. And it'll still compile, but obviously it's not going to be published because I can't mutate it. So a little bit of demo, it's kind of nice, but the really interesting thing with Compiler Explorer is not just that you can run an interpreter over the code. The really interesting thing is that it has, I'm at trace file. It has this tool called trace file, and this is going to actually trace the interpreter as it goes over every single step of the semantic evaluation of the program, right? And this is incredibly detailed. In fact, this is kind of impossible to even look at. I think we need a better way of looking at this. So let's try something else. So if you go to Compiler Explorer, and you can go to Compiler Explorer right now, this should work. You can load up Carbon. We have some sample code in Carbon. And it compiles. Okay, I'll refresh this just to make sure this is actually working. And if I have a typo here, right, it says that the compilation failed. But I can square something, and then over here on the right-hand side, you're going to see this trace. And so it's basically allowing you to explore the semantic interpreter as it works over all of this stuff. So it's doing all of these implicit conversions. We have heap. There's a lot of information here, right? And so this is an incredibly detailed view at exactly how the compiler models the semantics of your program. But notably, like, it does actually compute 12 squared. So we're at least doing math correctly. One piece of math correctly. So that's kind of our demo implementation that we're playing with. You can check it out on Compiler Explorer. But we didn't actually answer our question. I don't know if anyone noticed that. Like we don't actually have an answer for what comes next for C++. I mean, to a certain extent, probably C++ comes next for C++. I think C++ is going to be here for a very, very, very long time. And probably some of these really great garbage collected languages should also be part of what comes next. And honestly, Rust should be what comes next for some projects. If you can use Rust to get your project to work, it provides tremendous advantages. And so we've actually been asking the wrong question, because it's not really like there's one thing that's going to come next for C++. The real question is Carbon a part of what comes next for C++? And unfortunately, the answer is still, I don't know. I don't know yet whether Carbon is part of what comes next. I'm very excited about this direction. I think it's a really exciting way to improve things. I think it's a really exciting way to bring the C++ community and code bases along with it. But I'm not going to be able to answer this question. All of the screen full of people working on Carbon can't answer this question. That's actually why we're here presenting, right? We're here because we need your help to answer this question. Right? We need you to help us build and shape Carbon, because we are a long way from done. We need you to help us evaluate it, to tell us what parts are terrible and how to fix them. We need you to help us fix them, right? And only once we've actually built this out and we can run an experiment and really evaluate it, are we going to have an answer. And so what I'm really here to do is not to answer this question, but to ask you all to work with us together to find out if Carbon is part of what is next for C++. So thank you very much. So with that, we have an exceeding amount of time by design, because what we're going to do is we're actually going to bring the 3 Carbon leads up onto the stage and allow you all to have kind of not just a normal Q&A, but a full discussion with the 3 Carbon leads. We also have some other folks that work on Carbon in the audience. If we get stumped on anything, we'll drag them up here as well to help out. But this way you can ask any questions you want. We can dive into anything you want. And hopefully my other leads will join me up on stage. I don't know if you want to sit down. I think I'm too pumped. Microphones. So, questions, or are you all like, no, we have no questions? We do have microphones. We'd really love for you to come up and ask questions at the microphones for the recording, so we can build some nice long queues here. Do you have a preference, left versus right? Where do we? Okay.
I have a question. How is Carbon going to stack against C++23, C++26, and C++30 that we are envisioning is coming up? C++ survived 30 years, so I'm sure that it's going to survive another 30 years. So how you are going to compete?
I mean, my goal isn't really to compete. My goal is to try and explore, things that we aren't able to do with C++. And so I don't think C++23 or 26 or 30 or 40 are going to completely change the grammar or introduce a novel generic system. And so in some ways, I think we're really trying to explore alternatives that aren't available in a kind of backwards compatibility prioritizing world.
See, like I already see some of the Carbon features are already is coming in 20 and C++23. So like concepts. In concepts, you can actually define what the template types is going to implement, right? So like you have a nice definition that this summary will have a method like summarize. We can define this kind of templates using concepts. So why should I use Carbon?
I also, if you all want to talk, just like talk. But I think the important thing to realize is that concepts don't give you generics. So even though you can define what signature your type should have, you can't type check against it. It's not a complete system for actually doing definition checking. And that's one of the unfortunate things about concepts. So you can't do that, and there's no way to do something like the external impulse, right, where you can't use it as an extension mechanism.
One other thing I would say is, while C++ does have a huge head start on us, one thing that Carbon has is the ability to move a lot faster, because we don't have to go through the committee process. We don't have to have a minimum of 2, 3, 4 committee meetings, which will take 1.5 to 2 years to make a decision on a design change.
Hi there. So I imagine question one, when this hits the internet, if it hasn't already, is about memory safety, which is, of course, Rust's big selling point. So
Yes.
are you able to talk about that?
Absolutely, that's a great question. So memory safety is really, really important today, of course. I think the key thing to realize is Rust is kind of taking memory safety as their starting point, right? And they're working down to make a more and more ergonomic and accessible language. We're not doing that, we're taking a different approach. We're starting with something that we think is interoperable with C++. And unfortunately, C++ is very unsafe. And so that means that we're starting from a pretty low bar. But our absolute goal is to basically start there and build up as much memory safety as we can add into the language. It's kind of a bottom-up approach instead of a top-down approach in terms of like starting with something that's close to C++ and that we're completely confident we can interoperate and migrate to, and then adding interoperability where we can find ways to do it that don't break that. There are some really great folks, including at Google, working on Rust to see if we can work the other direction, starting from Rust and building better and better interoperability between C++ and Rust, to see if you can maybe get there through that path. And frankly, if they succeed, that would be fantastic, right? That'd be a great outcome in my opinion. But we don't know that that's going to work. It's very high risk. And so we also want to explore the approach of kind of starting from where C++ is and just adding safety as we can and where it doesn't really break interoperability with existing code bases. Long term, we definitely want to get to at least as much safety as something like Go or Swift has, if not all of the concurrency safety that Rust is able to provide.
Hey, awesome effort and awesome initiative. Congratulations! Like it really looks really good. And to be honest, I'm excited to see where all this goes. It's just the start. And thanks for sharing that with us. I appreciate it. A quick question. Any thoughts about the tooling ecosystem? Can we reuse tools that were built for C++, like Clang Analyze, things like that, that work on the AST in the Clang and things like that?
Do you have thoughts?
I think probably not directly. A lot of those tools are very tied into the exact representation of the Clang AST. It may be possible that there is some way that we can reuse those or extend them to work on a combined Carbon C++ program.
Awesome, thank you.
Hello, thanks for presenting, Chandler. That was really quite exciting. I've got lots of questions. I think the first question, though, is that C++ has no reflection story. Do you intend to have one in Carbon? And if so, it seems to me that's going to create some significant interoperability barriers. Any thoughts?
I think we've been thinking about reflection a lot and metaprogramming a lot, but I don't know that we have a concrete plan in place. That said, I don't think it's going to create too many interoperability barriers because if you're doing metaprogramming in Carbon, you're kind of going to, at the end, produce something that still, exists in the Carbon world and semantic model. If you're doing metaprogramming in C++, you're going to do something that exists in the C++ world and semantic model. And so if we have good interoperability between those two semantic models, we should be able to have interoperability even between metaprogrammed semantic models within those worlds. And the whole idea of using a genuine C++ frontend to kind of parse the C++ code should let us run the C++ metaprograms kind of faithfully as they would have in C++. And so I'm not massively worried about that. I mean, I think migration might be a bigger challenge there because metaprogramming is a huge barrier to kind of tool-based transformation of code. So I would be much more worried about things like migration than interoperability when it comes to metaprogramming.
Okay, thank you.
So in your slide, it was mentioned that there is a CLA. So who do you sign the CLA to?
It's a great question. Right now, we're bootstrapping with Google CLA, but the plan from Google is to basically, as soon as there's a foundation that makes sense, an independent foundation, we'll transfer everything over to that foundation. We're following the same model that Kubernetes and a few other major open source initiatives have followed. Or they have to start with some entity holding the CLA, and then once there's kind of an independent foundation, they transfer things over to it.
Because having a CLA at all is like a hard blocker for many people. So this is problematic. So maybe think about how that's going to work.
I mean, I really do understand, like, CLAs are a huge issue. The challenge here is that our experience with other open source projects is that not having a CLA places the project in a really untenable position where they can't fix bugs in their license if they're ever discovered. They can't make any changes if they need to. Certainly any change to the license is something we're gonna take as a very serious step and be very reluctant to do it, but it seems important to kind of have that capability when it's needed.
What were some of the programming languages that you draw inspiration from? Or do you just start off with C++?
I mean, I certainly start off with C++, primarily. That's also the language I know best. I don't know if you two have others.
We definitely looked at Rust a great deal. We looked at a lot of languages that are in a similar space to C and C++ in terms of not being garbage collected. There's various new ones, for example, Zig.
Yeah.
I personally took some inspiration from Haskell, but probably the right amount, not too much.
Also, I think Kotlin, for example, the members being public by default was something that I think Kotlin did, and like we saw, and it actually was remarkably clean. I don't know if there was
also Swift.
Swift, yeah. The generic stuff, like a lot of stuff from Swift also.
And some syntactic ideas from
Yeah, a
Swift
bunch of
as well.
syntactic ideas. So lots of different languages.
Hello. You mentioned, I think you have some interesting concepts regarding parameter passing. One is that value and constref is essentially the same thing. I think that's good. How do you protect against aliasing? That's my first question. And then there's a second one, but maybe.
I mean, I think aliasing is a big challenge here. One of the interesting things we found is that you can create this bug with const references today in C++.
But you at least you know. Or you actually, you can find out.
You can. So we actually ran experiments where we would like force copies and other things to see if program behavior changed. The surprising thing was that people don't tend to write this bug. We have not found like a really massive amount of this bug being written so far, but we are definitely thinking about ways to kind of, tighten down the aliasing long term if we want to just try and make this much more precise.
I'm perfectly willing to believe that it's rare. The other thing is, you said that basically mutable things are always passed in as a pointer, which I like. Pointers have the problem that they're nullable and they're incrementable. How do you go about that?
Well, by fixing that.
Okay, just that's what I wanted to hear. Okay.
So we make pointers not nullable and not incrementable, and then they aren't bad.
Okay.
But it's a great question. It's a great question, right? Part of what we are able to do when we leave the legacy behind is we're able to look at this and be like, this is a great idea for how to do indirection. It's just it's also combined with some ideas that are not as good or would benefit from different representations. And so we can have an optional pointer for null. Right? And we can have some kind of slice type or range type for the thing you actually can index and increment.
So the pointer is going to be non-null by default, and if you say optional deep pointer, then you get a nullable pointer.
Yeah.
Cool.
Hi, great idea, great project. I wanted to ask if you have any plans on the evolution of libraries. How are you going to define a fixed API for it, or we are going to be in the same situation we are now, that backward compatibility of libraries is really hard?
Well, so I think there's probably two different parts there. One of them is library ABIs, and our perspective there is to try to avoid having a fixed Carbon ABI, in the sense that when you build a Carbon program, you build the entire boundary of that program and everything within it. So there's no ABI splicing issue there. And then to have some mechanism for defining a stable ABI that would be used in the case where you actually want a hard ABI boundary and you want to be able to have two pieces moving past each other and separately compiled, which we are hoping is going to be a rare case. The other part of it is the source compatibility side. And we have lots of tools that we've already built for dealing with that, for things like, suppose you want to change what's in an interface, how do you do that in a way that's forward and backwards compatible and gives people a chance to port? And then there's going to be some tooling-based ways of migrating between libraries. We don't have the GSLs that completely worked out yet. But I'm certainly hopeful that whatever mechanisms we build to, say, be able to migrate from one version of the language to the next will also be available for people writing libraries, both the standard library and their own libraries. So you can say, when I'm doing this migration, here's a tool I provide to my users in a really easy way. So they can just say, I want to go to the next version now.
It comes down to what the goals are. You know, earlier when Chandler said, but pointers aren't going to be nullable, in the same way we're going to say, but we might break your old code, but that's fine because we have a tool to fix your old code when we break your old code. It's a different goal around not being handcuffed by, we have to support your old stuff.
My question comes from the side of those libraries you don't have the code. This migration tool will help on those too? For example, something you got proprietary.
I think there are two cases though, right? There's a C++ library that you don't have the code to. And we are looking at how we can interop with that. It's a more difficult interop problem, but we are looking at that. And then there's the case of shipping just a binary library as some kind of product. And there I think what Richard mentioned around having some explicitly stable ABI mechanisms in the language that you can use across those boundaries. Have the rest of the language not have an ABI, but have something that's designated like, no, this type and this method, they have a specific ABI so that I can use them in a kind of plug-in interface boundary, and I can compose things that way.
Thank you.
Hi, you mentioned wanting an integrated or standardized package manager, but what about build systems? And how do you see that working with C++ Interop? Like I noticed your example was using Bazel.
Yeah, so on the Bazel point, just for clarity, the reason we're using Bazel for the actual project is just because it has really good support for testing and especially fuzz testing. It's not meant to be indicative of what anyone else would necessarily want to use. I think, so my personal opinion here is that we can't afford to ask people to both start adopting a new language and switch from one build system to another. That will be a step too far, especially because build systems are much less incremental than languages, right? I can have a build system that potentially supports two different languages, like C and C++ today. I can't really have two build systems and graph them together, or if you do, it's really messy. And so our goal is to really meet people where they are with their build systems. We're going to try and have a compilation model that fits into existing build systems very, very cleanly because we just think that that's a necessity to be successful.
And we want to interoperate with not just the C++ language, but also the C++ ecosystem, and that means we have to interoperate with existing build systems.
Okay, thank you.
Hey, thanks very much for the talk. That was really interesting. Regarding Interop with C++ and the adoption and the migration story, just wondering, are there like any barriers to like what versions of C++ that you'll be supporting or could be supported with Carbon?
I think our current thinking is C++ 17 is our baseline, but we're open to changing that based on what the community needs. Yeah.
Okay. I would like to talk about governance.
I'm here for it. I was wondering, we got all of these great language, like, yeah. I'm a language nerd, so don't get me wrong. I'm a fan of this entirely. But I was wondering if we're going to talk about governance too.
Yeah. So you have exchanged a glacial governance model for something rather more nimble and agile. But it does feel like a benevolent dictatorship, which, you know, has had successes. I wondered if there were any other, well, okay, which governance models did you discard in favor of this one? Sorry, that's the unkind way of asking.
No.
But I think that is the one that we want to know. What did you set aside to come on top with that one?
Yeah, so we definitely considered benevolent dictator single, and we decided to scale a little and to have some diversity of background and opinion in the governance group. And there is also an intention to be able to adjust that as time goes by. Yeah. You know, it's not going to be the three of us forever.
I definitely am looking forward to having rotations. My long-term goal is that we end up with like a pretty solid bench of people who are all like have been a lead and are happy to step in and be a lead. And it's just that there are three of them at the moment. But like if one of them is like, I'm gonna go on leave for 6 months, there's like, yeah, it's fine. There's someone who's gonna be in great shape to step up and fill in, so that we have the scale. I think you had my favorite comment though. It's like a benevolent dictatorship, except, you know, not as much of a dictatorship and not as much for life, but hopefully still benevolent. We did actually discard some though. So one thing that we tried early on was we tried having a more layered consensus model with like a kind of 3 different tiers of escalation and like small groups. This is actually something we've spent a bunch of our time experimenting with early on, even though we didn't need it. It's a small group of people because we wanted to understand what governance model to use. And they basically were all too slow and annoying, to be honest. The reason we ended up where we did was because we kept seeing the need to drop down and have a lighter weight model, move faster, be more agile, be able to respond more rapidly. And that's what actually pushed us all the way to like 1 step above like a BDFL, right? We didn't want to go down to a single point of failure, but just 1 step above it.
Why choose a tool-based transition to a new version of the language? Because there's an immediate downside that I can think of is that sometimes a project is kind of done. You don't need to edit it anymore. And, well, and also you can use tools that will maybe take time to update. And the package manager, the eventual package manager, we'll have to kind of resolve that in a way too. And I've been thinking, is there a reason why that instead of something like epochs?
I mean, I don't think it's that. It's either epochs or tool-based upgrades, right? Tool-based upgrades are something you might use with epochs to move from one to the other. Okay, and so these aren't intention. And I think that having something like epochs makes a lot of sense. Having additions or something, some amount of versioning in place so that you know when your transitioning is good and you have tools to kind of empower you to do it efficiently. But I guess I'm not a big believer in projects that don't need to be edited. I think that they still have bugs that need to get fixed. And most importantly, especially at large scale, they're going to need to update their compilers, their tool chains, because hardware platforms change and evolve because of security problems. And if you're going to do that, you're almost certainly going to have to change the code anyways. We find very little code that truly never needs to change, even when we're updating a tool chain. And so it seems reasonable to also plan to have some cadence for updating with the language. That said, churn is a real cost, and so we don't want this cadence to be unsustainable, right? We're gonna have to look really carefully at how we slow things down enough that people can actually ingest the changes in a healthy way and not in an unhealthy way. There is a balance there, but I don't think that stability, like the extreme of stability, is the right kind of quiescent point. I think that there's a balance above that that's gonna be more healthy.
Thank you.
So we're probably all at different points in our experience and our careers, but if we're interested in helping, what are the ways that we could get involved in helping?
If they show the slide again briefly. I don't know if they can show the slide again briefly. I'm sorry, I caught you all off guard. So we have a GitHub project and we have a Discord, and you should be able to go and join them right now. They're all public and live. We do have some issues in the GitHub project that are kind of starter things, and that's something we actually actively want to expand to have more starter projects and other things to help out with. If you are on the Discord chat, the other thing I'll say is there's a constant stream of ideas and questions, and just being around and giving feedback on them is actually surprisingly valuable. Having people to be like, you know, like that me keyword, it's kind of weird. Maybe you don't want to do that, is actually really valuable, so.
Yes, one question.
It's your turn.
Oh, it's your turn, go for it.
Yeah. I have read a paper about C++ where an author is trying to use reflection and inject function on the runtime, which is similar to like the concept you have introduced in the template, that you can actually modify the external classes and inject new functions. So it looks like that many of these things that you are talking about in Carbon, it can be also implemented in C++. So why you are not trying to make C++ a better language?
Yeah. So I think that there are two things there. I'll answer one of them. I don't know if Richard or Kate want to answer the other one. The first one I want to answer is, we've been trying to make C++ better for over a decade. I don't think we're going to stop. I don't think that the C++ Standards Committee is going to stop working anytime soon. C++ is going to keep getting better. That's not the goal here. The goal here is to see if we can make more dramatic changes by changing the priorities, by changing the assumptions that we operate under. And the changes we're talking about are things that you cannot do with any form of metaprogramming. You cannot redo the keywords and grammar structure with metaprogramming, right? That's already fixed. You can't introduce a definition check to generic system through metaprogramming. I think actually there are languages that have tried. I think Scala tried at one point, and it was very bad for users. Like this is incredibly difficult to do through metaprogramming. And so we are actually chasing things that I think are significantly outside of what you can do with metaprogramming.
If you look at the differences between Carbon and C++, some of them are like, oh, C++ is missing this thing, we should add it. But a lot of them are more in the category of the all our defaults are wrong category. And you cannot change the defaults in C++. Like we cannot say, oh, constructors are all explicit now. You can't. The fundamental rule is no breaking old code. When you take that rule away, some very cool things happen. And it's not about a deficiency, it's about priorities and goals.
Hello, me again. I was looking at your list of C to C++, Java to Kotlin, and the idea of successor language. But you're talking about a successor to a successor language. And I wondered if you could, I was struggling, I mean, Connor might be able to help me out here. Where is he? There he is. Can you think of any successors to successor languages that have succeeded? And like, I'm not going to count BCPL here, because I think C and BCPL are...
See, I was going to go to that one. But no, Swift, I think, is a great example, because Objective-C is technically a successor to C. Objective-C was an attempt to bring Smalltalk and the features of Smalltalk and make it available with the C ecosystem by being a superset of C, but adding a Smalltalk-like set of language features. And then Swift has again done another level of successor after that.
Okay.
I can't think of another one.
Thank you.
Well, on a slightly different scale, different versions of languages behave like incremental successor languages in a lot of ways.
Can you tell us anything about what you're doing to make the community a healthy environment?
Yeah. I mean, so the first thing we're trying to do is we have a code of conduct in place. We're actually trying to uphold it really, really carefully. We're trying to give really clear, just kind of heads up to people joining the Discord to try and set the tone there. We want it to be a super friendly one. But I think the biggest thing we're doing is we're actually, so we're working with Celine, who some of you may know from other C++ events. Celine Dedudge is actually on our team and helping us figure out exactly what we need to do to really set the community up to be successful. And she's working on this. She has a whole pile of plans. I don't know if there are any particular ones worth calling out.
I think just, explicitly having goals around community for us, that when something is happening, we're not going to run into the paradox of the brilliant contributor who's also toxic, because we have rule 1, you don't be toxic.
Yeah.
So partly that means making an atmosphere where people don't feel safe to be toxic, so they scale back, but also means that we've already made some decisions in advance about priorities.
So this is really cool sounding. So one question is so very occasionally you need to drop down and do, compiler intrinsics or that kind of thing. So is there a facility for that, or is your philosophy purely hide all of that kind of stuff and don't let people use it?
I don't think there's anything we've explicitly designed in that space yet. But certainly we expect to have the full power of the machine available there. So if you need to drop down, we'll provide you with mechanisms to drop down, much in the same way that C++ does.
One thing I can say concretely is that one of our principles is that all of the APIs are library APIs. And so we want to be able to define, for example, all of the APIs you use with an I-32 in the library, but we then do have to implement them. And I think in a lot of cases, we're going to expose some of the pieces of that implementation from the compiler directly into your code as well, so that if you're implementing something really subtle and weird at the low level, you're actually going to have access to the compiler. I'm a big fan of giving that access to the compiler when we can.
Yeah, hi, this is really exciting stuff. I do have a question. So one of the strengths of C++ is actually that it's targeting a lot of platforms, right? So we have 3 or 4 major implementations of the compiler. We have C++ running on Linux, macOS, Windows, Android, iOS, all kinds of embedded devices, bare metal, real-time operating systems. We have lots of custom compiler tool chains for those embedded systems, which might not even be built on Clang. They might be built on GCC or EDG frontend with some completely custom stuff. And it's one of the strengths of C++ that it's running on all of these things. So my question is, how much of this kind of community are you actually targeting? Like when you talk about different platforms in terms of hardware, like what slice of the C++ community are you targeting with this project?
I'm just going to mention, and I said I bring diversity to the leads. Probably my most important diversity is I'm the Windows person.
It's an important point. I don't know if you want to. I think that the key thing here is some of this platform diversity, I think, is kind of a longer-term question. I think before we really invest too much in the platform diversity, we have to know, again, like the answer to my question. Is this actually a part of what we want to have next for C++? And until we know that, doing too much investment may not make sense. But I think that's just a question of investment, not scope. And I think in terms of scope, we're pretty open. I think the biggest thing that we want to focus on in terms of scoping is cases where performance is actually the top priority. I think there are a lot of cases where something else would be the top priority. And maybe for those use cases, a different language is actually a better tool for the problem they're trying to solve. The other one is modern hardware. I don't think we want to try and really support a lot of very old hardware architectures. That we want to be a little bit more forward-leaning. And I think that's mostly because it's going to take us 5 years, right? Like this is such a long-term project, it doesn't make sense for us to worry too much about older architectures. But in terms of the breadth of platform within the modern space, I think that's something we have to tackle long-term.
Okay, can I rephrase my question real quick? Like,
sure.
How much does it depend on Clang specifically as the front end for this?
Oh, that's a better question.
I would say really not at all. The Interop you could build with EDG, you could build with GCC. There is nothing truly Clang specific going on in there.
A little bit up with the mic.
All right, thank you.
Oh, look, it's me. Hi. It's nice to see you. It's like seeing old friends, isn't it? Actually, I have a potentially facile question. Can we have a drawing library, please?
Can we have a drawing library, Kate?
I'm not going to argue against it.
Okay.
I've argued for it in other contexts.
I think the scope of the standard library is something we really haven't explored at all. And if you want to, as Kate's saying, right? If you want to influence,
That's the lead-in, yes.
Yeah.
I think one of the open questions we have is where do we draw the line between the standard library and things that are provided by external packages? I think a lot of that's going to depend on how easy we can make it to pick up and bring in external packages versus things from the standard library. So certainly, I would want there to be a de facto standard way of doing that kind of thing. I think that's really valuable. But I don't know whether that belongs in the standard library or somewhere else, and that will depend on a lot of factors.
We're still really settling some keywords, but please come and be part of the conversation about library content.
Okay, thank you.
I was going to ask about the STL, so.
So my first question was actually his question, so about the standard library extent, but I also had a second question. So what about the implementation? Do you guys plan on having more of an opaque implementation that very compiler, like inside a compiler, or is it going to be more like C++, where it's all implemented as C++ code? So in this case, would be implemented as Carbon code, where I can just I don't know, like in Visual Studio, press F12 and read the code and just re-implement it myself if I need to?
I think mostly the latter. The whole idea of having all of the APIs be library APIs, I think, leads us down the path of having a relatively small interface layer between library code and the compiler itself.
There'll be certain things that are primitive, of course. Like you won't be able to read the implementation of plus on I32, but at higher level things, yes, absolutely.
I still think we could.
Sure, we could.
Thank you.
A lot of modern languages, even beloved languages like Haskell or Rust or Scala, tend to grow more complex over time, and one of the advantages seems to be that this is less complex than C++. How do you plan to manage complexity as the project moves forward?
I actually think our willingness to break old code is going to help keep us simple. So every time C++ adds a keyword, they have to support all the old code that existed before that keyword was added, and you get this divergence of don't forget to add no except, don't forget to add this, don't forget to add that. And if we can change what the defaults are as we go, you don't have to remember to add things because the defaults will be the right defaults.
I think there's a related thing where a lot of complexity comes from features that interact. And unexpectedly. And the reason that this creates so much complexity is because you don't want to change the existing feature as the new one comes in and the unexpected interactions are discovered. But again, if we're willing to break old code, we're going to be more able to really look at those interactions and see what the simplification would be to merge them and mesh them nicely. Some of them, I think it'll still just get more complex. This is not going to be a simple language. Like realistically, this is not going to be a simple language. It's got to support the C++ use cases. But I think we're going to have a lot more tools to curb that growth than others.
Not really a question, I just wanted to let you know that there's already quite a lot of buzz about this on Twitter as of like the past 30 minutes, and several of the Discord servers I'm on, completely unrelated to C++, are blowing up with the Rust community is all over this. This is like 30 minutes of this already.
Okay. Hopefully good explosions, not bad explosions.
So I wanted actually a bit of a follow-up to Z's question, right? Like C++ provides effectively infinite stability long term. And on the other hand, like providing no stability, like changing the keywords in Carbon on a daily basis, that, right, like at the extreme, that's also sort of
benevolent.
That's fair. But I guess the question is like, are there any ideas for what time frames look like for what stability would be, or how we make decisions so that we can guarantee that they are benevolent? Like, how do we make that trade-off between, yeah, this is actually going to be a little bit painful for some people?
I think that's going to have to be a conversation with users as we have users. And again, this is years away, right? Right now, we don't even know if this is a good idea at all. If this is a good idea, then we're going to need to have the conversation with users to talk about what the rate of change is that's sustainable. I have no idea what that rate would be.
We absolutely want to be listening to users when they say, no, you're going too fast, this is too much change. Or if they're saying, no, we want the new features. Don't worry too much about the change.
Are there already thoughts on domain-specific languages? So like the operator overloading C++ that's been abused for domain-specific languages versus this explicit D, you kind of print your own source code. Any thoughts on where this is going with Carbon?
Do you have any thoughts on
this? There are lots of interesting options to pursue there. I don't think we have anything concrete worked out. We will have operator overloading support. Not just because we want to interoperate with C++, which has that, but also because we want to enable people to define like really rich, useful abstractions, which will require that kind of thing. I don't know necessarily that using that to build a domain-specific language is the best approach, so maybe we do want something that's more like what other languages have done. I think Rust has done some interesting things in this space with its macro system.
Yeah.
Hi, how will you all handle undefined behavior, especially with respect to the interop?
Well, it's undefined. Sorry, I couldn't resist. I think our goal is to really have as little undefined behavior as possible within Carbon, but at the interop boundary, we have to deal with where C++ is and where the compilers that implement C++ are. And so it's just kind of the reality that we have to interface with.
But how will you avoid every call into a C++ object being UB? Or will you look somehow past it through the layer?
I don't follow why would every call to a C++ object be UB?
Well, just that C++ contains so much UB, you know, any call down, unless you look at the C++ code, could have UB in it.
I mean, it could. Our goal is to not change how that C++ code works today.
Okay.
Right, we're going to use the same compilation strategy that we use today with the same tool chains. In the future, maybe even multiple tool chains. But the whole point is to use already working technology and already working C++ code. Maybe it has UB, but it is working today.
Right.
And we shouldn't make that worse.
Got it. Okay, and it's not a 0 UB in Carbon. It's a limiting UB in Carbon. So
I think pragmatically we can't aim at 0, especially if we want to interoperate and migrate C++ code. It's just not realistic.
One thing that we can and would like to aim for, though, is if there is UB, that we'll provide you with a way of checking for it. We don't want to have unchecked, undiagnosable UB.
I think we are out of time. I think I'm getting the sign that we should wrap up here. But there are several folks who are working on Carbon, and they are here. And so I was going to try and have them kind of drift up on stage and introduce themselves, so that if you're looking for someone to talk to about Carbon, feel free. Sadly, one of the folks, David Senkel, is not going to be able to be here. But if you see David Senkel after this conference, you should also talk to him about Carbon as well.
Hi, I'm Josh.
Why don't you, Josh, could you tell us a little bit about what you do on Carbon?
I work on generics, classes, and other parts of the type system.
I'm Jeff Romer. I'm currently working on variatics. I've also worked a bit on some types, and keep trying to work on error handling. We'll probably continue to do so, and various other things.
Hi, I'm John Ross Perkins. I kind of pick up the loose ends. I've been working on Explore and the tool chain and stuff for GoPublic and our infrastructure. So more or less what needs to be done.
Yeah. And thank you all. I really appreciate you all having us here, and really excited to keep this conversation going.